Today we're going to see a new, you see, or different difficulty that you will find with modeling systems. And that is, on occasions, you will have the equations with algebraic loops. And you might be writing the equations, and you come to a loop and you never-ending derivation, and there is a problem, obviously. So we're going to identify what the problem is and also identify and suggest the solution, and in this case an automated solution. So let's examine this. So this is the algebraic loops, and what we will look at this outline. What are the nature of algebraic loops? Just like we have just understand the nature of derivative forms, we want to know what the nature of algebraic loops are. What are we understanding what about the constitutive equations of algebraic loops? What is the generation of system equations when you have algebraic loops? What we would like to do is that ChemG will first of all detect the algebraic loops. Two, that there will be form that we will be able to transform those implicit equations into explicit equations. And then finally, we would like to take a look at the physical meaning of algebraic loops, just as we have looked at the physical meaning of derivative forms. So in this case, let's look at an example like this. And if you enter this into ChemG, you are going to be surprised. Well, it looked like a simple system here with 3 loops, some resistors, inductors, and a capacitor. It turns out that we have this kind of difficulties, because if we were to draw the zone graph and try to complete the derivative form and to complete the causal form, this is what will happen. Okay, hold on. I am going to try to complete the causality with and do it perhaps with a different colors, so that I think I'm going to use the red pen. There we go. If we assign the causal marks to this, obviously you assign it here, see, for this. You go in here and you assign this. Okay, but you cannot make any progress because none of these two are defined. And this one, and here you put, and you still cannot make any progress. And you put the C element over here like this. So I am going to draw in red. ChemG will do this, exactly what I'm doing right now. It will flag you, it will actually draw lines like this. This is the image that you will see in if you put this into ChemG, like that. And the causality does not complete. So in here the problem is different than in derivative form. In derivative form the causality completes, but it has derivative form. Here we have a different situation. The causality doesn't even complete. So unless we find a solution, and inside ChemG there is some way to do it, we're stuck. And you see the circuit doesn't seem to hurt, yet we have this problem right now, that the causality does not complete. So we are going to see what we can do about this. You see, in here, one possibility is that we assign the causality for one of the elements. See, let's say that we assign it over here like this. If we assign it over here, then it completes here and it does this. This is if you assign the causality here, but you could also assign it here. And by doing that, what will happen? If you assign it here, see, these ones in dotted lines are not complete. And so you will have, in this case, two algebraic loops, and in this case, one algebraic loop. So depends on what you do. You say, oh, our elements could take any causality, so I'm just going to assign it to one. And if you do that, in this case, it fixes everything. If you do that in this one, you assign it here, no, the other one too. So you will have to make two assignments. If you have to make two assignments, then obviously that's not going to work. And in here, if you assign to the one on the left hand side, to this one, sorry, here we have a little bit of a difficulty. If you assign it, here's where we were. Yeah, if you assign it to 1, you're going to have this kind of equations. You assign it over here, and you of course try to find the derivatives over here, and this is what would happen in this case. This system that you see here is an implicit set of equations, because this E2 that has been, or F2 in this case, that has been in here is, you see, this one is the problem right here. See, you say F2 is E2 over R2, and then you say E2 is E1 minus R3, and E1 is here, and E3 is here, and you continue, and you'll come back to this forever and ever as in a loop. So that's why we have this this problem. So it is an issue that presents a difficulty in the equations. So if we derive the equations, obviously you have these three derivatives, but you see this variable f2 is the one that you assign over here. It's an additional equation that we need to derive. Otherwise, these are implicit set of equations. See, f2 is in all three of them. So if this is true, we need to find out an equation for f2. And having done that, then we will be able to solve it. If we go on the other alternative, where we assign it here and we also assign it over here, and you derive the equations, you are going to require these two equations. One for FE2, that is the one assigned, and the other one for f sub 6, which is the assigned here. And in this case you have two algebraic loops. That's why you need two additional equations. So that is the problem. So what is the ChemG solution to this algebraic loops problem? This is the first problem. As I suggested to you, ChemG will come back with this kind of causality, and it will actually put all in red the path that doesn't know what to do. ChemG doesn't know what to do with this, because it's telling you, look, you know your system, if you continue like this and you produce implicit equations, unless you have an implicit equation solver, the system is not going to go. And so it's actually a good thing that warns you, because now you know what to do. If you put this here, then this still needs to be resolved. And if you fix the other one, then everything is cool. So, but we needed to specify two variables. That means to solve the loop, we need to specify those two equations independent of the others. So for that reason, I wanted to show you other examples of this problem. When it happens in a bond graph model, you have to think that the same thing. Either we specify something too many, is already specified, or we also need something into it. So that is very important concept, because it allows you to think on what to do, what to change to fix your system. I have a model of a valve of a combustion engine, and for purposes of this explanation, I am going to use this that actually has how many loops? 1 on the left, 2, 3, 4, 5, 6, 8 algebraic loops. Meaning, see, the system looks at it and does the causal marks on the normal sections, but it doesn't do it on the other sections, because it's all undefined. That's the problem. When you have algebra loops, you have the problem is undefined. So if this is true, here comes my thinking. In here I say, these are the equations that I got. And this E2 and F6 are the ones that I assign. So to be able to solve the system, we must find E sub 2 and F sub 6 as functions of the states and the inputs. So there you have it. You have E3 F6 and E6 as the outputs of what we want. This is what we want to study. So you see, this is your original system, but in this case you have your original system plus this j times a, which are the vector of algebraic variables. And so this a is kx times lu times m times a. It has that form. So if you manipulate this and you put what the value of a is, we have resolved the algebraic loops, and then you can calculate the new A, B, C, and D matrices. So you see here, you have, once the loops are resolved in the system, we can calculate based on these new matrices and come up with an explicit set. What is this doing physically? It's actually combining elements to come up with the solution. And so you see the A and B matrices are a combination of these, and those are the new A and the new B. But now the outputs, y is equal to cx plus d plus O times A, which is the matrix times the variables that have been assigned. We found that the solution of this algebraic loop for the variables, if we use the matrix n and the A vector, we will have this. So the y and vector of outputs, it has C and D original plus this other part of the equation. So in that case, you will come back with a C and a D that are new. I did an example of this to obtain those matrices using the CAMG software, because CAMG will let you proceed with algebraic loops, although it gives you a warning. But then you have to do those matrix manipulations to be able to get it in this form, the state space. And the symbolic manipulations can be quite large. Look at that denominator of the transfer function. This is the numerator, but the denominator in most here we have the very long denominator. If you put the numbers, of course, it's easy, like the one down here. And then you will have the time domain display and the frequency domain. Frequency domain is the when you have an input and you test the system many frequencies until we can get the plot between the time and the display, or the other one is going to be the magnitude versus frequency. Physical meaning of CAMG solution of algebraic loops. So now let's turn a little bit as to what physically it means. Yeah, in here you have this model on the right of this valve. This is an internal combustion engine valve, okay, and it has all little inertias and everything in there. So this is normal and everything is cool and no problem. So I am going to begin changing this. See, you see, instead of doing this, I'm going to suppress these two masses and see what happens. Look, you created this algebraic loop, and you have it modify this in such a way that they really are not two but one. So this idea of putting redundant elements inadvertently, it is the source of these problems of derivative form and now of algebraic loops. But you see, the system really is not like that. It's like this. I am doing this to illustrate that if you did not specify those, you will be getting this kind of problem. See, here I made a change for the bottom ones. See, take a look here. Instead of 6 masses, this one has 4, and now this one has 2. So you have even more derivative forms. What are the conclusions of this? First of all, we have a computer-generated algebraic loop in the CAMG. This is possible for a single algebraic loop or for multiple algebraic loops. 2, the solution is independent of the system order or the number of algebraic loops. The solution is valid for linear and nonlinear systems. Opens the door for solution of a new set of systems. And of course, this is I always talk about the integration of block diagrams and bond graph models. And that is how we can understand this idea of algebraic loops. So I'll repeating here. If we go back and they was reduced to 2, and then it is difficult. So here's this 4, and this is 2. No, this is the one that is okay. Let's see, where is? Yeah, this is 4, and the other one is okay. So from 4 to 2 is that we went down. Okay.